All right, hi there, students. Let's move on to part two of using Newton's laws. This is where we start to incorporate kinematics. I'm just going to go through two example questions, and then I'll summarize at the end with a couple of key points. So just like in the last video, please watch this video and pause and try the questions yourself before I do them. And it's totally fine if you get them wrong, but it's more important and better for your learning if you try the questions yourself first. And if you don't know how to do it, watch the first little bit, see how I get the problem started, and then try it yourself. Just like, don't just watch the video without trying anything at all. Okay, so here's the first question. Starting from rest, an ice skater pushes the boards with a force of 130 newtons and moves 0.704 meters. That's while he is touching the boards. That's how far he travels. After that, he stops touching the boards, so he pushes off. He's no longer touching the boards. He then moves at a constant velocity for 4 seconds before he digs in his skates and starts to slow down. When he digs in his skates, he causes a net force of 38 newtons back the other way to slow him down until he stops. Okay, so there are basically three components, not components. There are three kind of like time intervals here. So there's first where he's pushing on the boards and he's accelerating, and then there's the part where he's traveling at a constant velocity, and then there's the part where he's slowing down. So you have to kind of in your mind separate those into three different sections of motion. So part A is to determine the acceleration of the skater. Part B is first of all, when he's pushing on the boards. Second, after he stops pushing on the boards, and third, when he starts to slow down. So acceleration at during those three different time periods. And then part B is how far does he move in total throughout all three components of that motion. Okay, so pause the video and try it yourself. So for the first part, when he is pushing on the boards, he is accelerating because he's pushing himself. He's applying a force to the board. The board is applying a force back to him, and so it's accelerating him. And the formula for acceleration is force divided by mass. That's Newton's second law. So you just plug in the numbers for force and the mass of the skater, and you should get 2.4 meters per second squared to the east. Part two, there are no forces acting on him. After he pushes off the board, there's no frictional force yet because he hasn't started to turn his skate to slow down. There's nothing propelling him forward, so he's just going at a constant velocity. That's what it says up here. And so therefore the acceleration is 0. And then part three, the net force, which is given in the question, 38 newtons, which he is applying by digging in his skate. That is the net force that's slowing him down. So once again, we can use force divided by mass, and you should get 0.7 meters per second squared to the west. Just note that this direction is opposite from the direction in the first part because now he's decelerating, which means his velocity is changing to be more towards the west, which is basically the same thing as saying he's slowing down since he's moving to the east, but his velocity is becoming more west. Okay, part B is how far does he move? And this is now where it becomes a kinematics problem. Over here, it wasn't a kinematics problem because we were only dealing with Newton's second law and forces. We haven't really started to incorporate things like velocity and distance and time and stuff like that. Now it's a kinematics problem. So you want to know how far he moves. Remember, that's the total distance he moves. So how far does he move while he's accelerating, plus how far does he move while he's at a constant velocity, plus how far does he move while he's slowing down. So we have to calculate distance 3 different times and add them all up. So first, determine the velocity with which he leaves the boards. And just like in a regular kinematics question, let's write down our givens. Remember, you always need 3 quantities in order to use the equations of kinematics. So here's what we know. We know that he's accelerating at 2.41. That was a result from part A. We know that he travels... excuse me, let me back up. We already know the distance that he travels while he's accelerating. That was given in the question. But in order to find the next 2 distances, we are going to need the velocity with which he leaves the boards. So So we know those two things. We also know that he starts with a velocity of 0 when he first starts pushing on the boards. And what we were trying to find is the final velocity. Now, just be really careful here in understanding what final velocity means. It doesn't mean the final velocity of the entire motion. It means the final velocity of the part where he's pushing on the boards, which means how fast is he going when he leaves the boards. So we can use the following kinematics equation because we know 3 of those things and we're trying to find the other one. So plug in the numbers to VF squared equals VI squared plus 2AD. And if you solve it, you should get 1.84 for the velocity. Next, we're going to find the distance traveled while he's moving at a constant velocity. That's easier because it's a constant velocity. You don't have to use the 5 key equations of kinematics. You just have to use the one equation of constant velocity, which you guys should all know. Distance equals velocity times time. So plug in the velocity that was obtained a moment ago, multiplied by 4 seconds, which was given in the question. That's how long he travels at a constant velocity, and he goes that far in that span of time. Finally, you have to find the distance that he travels while he's decelerating. And once again, this is another kinematics problem. You don't need to worry about force here. We have basically transitioned back to the first unit of the year, which was kinematics. So just put yourself in the frame of mind of kinematics. And here we go. So you are given, here's what you know. You know that the acceleration is negative 0.704. On the previous slide, I wrote it as positive, but I specified the direction was west. But in this, when we're doing it over here, we should use a negative for the acceleration because the other quantities that we're going to be using are in the opposite direction. So you need to put the acceleration as negative to make it work with the velocity values that we're going to be using, such as this one. So we know that initially, when he starts to slow down, he's traveling at this speed in the direction of east, which is why the acceleration needs to be negative because that's in the opposite direction. And the other thing we know is that the final velocity is 0 because he comes to a stop. So, and we're looking for, I forgot to write down here what we're looking for. We're looking for the distance. I'll just add that into the slide here. D equals question mark. Go back and change it to a lowercase because Google Slides annoyingly always makes it uppercase when I do that. And so we can use the same equation once again, plug in the numbers in the appropriate places, isolate for D, and you should get 1.98 meters. That's how far he travels while decelerating. And finally, add up all 3 distances, and you get a final answer of 10.1 meters. So in total, between accelerating, gliding, and decelerating, the skater travels 10.1 total meters. Question number 2. We have a worker pushing 2 large boxes across the floor from rest with an applied force of 160 newtons to the right, pushing on the larger box. So this guy is pushing presumably from here, pushing that way, and with a force of 160 newtons. The boxes are touching each other, so obviously when you push the larger box, it also pushes the smaller box. And the masses are given, 32 kilograms for the bigger one and 8 kilograms for the smaller one. The forces of friction are also given. So there's 80 newtons of force acting to the left on mass number 1 and 20 newtons acting to the left on box number 2. And here are the questions. You have to find the acceleration of the 2 boxes. You have to find the force exerted by the larger box on the smaller box, which is not necessarily the same as 160 newtons. That's the force being applied to the larger box by the person. Oops. And you have to find the velocity of the boxes after 4 seconds, after they've been accelerating for 4 seconds. Okay, so for part A, here's the free body diagram. This is a free body diagram of both boxes combined. So when you have the force being applied to one of the boxes, well, they're moving together because the one box pushes the other. And so you can say that the 160 newtons is being applied to both boxes combined. Now, you'll notice over here, the frictional force that I've labeled is also the combined frictional force, because there were 80 newtons acting on box 1 and 20 newtons acting on box 2. So the total frictional force acting on the combined masses is 100 newtons, which means that the net force acting on the combined masses is 60 newtons, because there's 160, but there's 100 of friction counteracting that 160. So the net force is 60 newtons to the right. The total mass of both boxes combined is 40 kilograms. And so finally, once we've done all those kind of totals, the acceleration is force divided by mass. So 60 divided by 40 is 1.5 meters per second squared to the right. And that's the rate of acceleration for both of the boxes, which is the same because they're basically like attached to each other. Part B, determine the force exerted by the larger box on the smaller box. Here is the free body diagram of the smaller box. So we know that the frictional force acting to the left is 20 newtons. That was given in the question. But we don't know what the applied force is, because the applied force that's acting just on the smaller box is not the 160 newtons. That's the force that's acting on the larger box by the person. So we don't actually know how much of that force is transferred through the larger box to the smaller box. But we do know now from part A, shoot, 1 second. I want to reveal this gradually. Don't want to ruin the surprise, no spoilers. So we do know that the acceleration is 1.5. And we know that the mass is 8. So that's where this formula comes from here. So if the mass of this box is 8 kilograms and the rate of acceleration is 1.5 meters per second squared, then the net force must be 12 newtons. But there are 20 newtons acting backwards, so therefore the applied force must be 12 newtons greater than the frictional force. So you just add them up, and you can get 32 newtons. Okay, so the applied force, the amount of force that transfers through the larger box onto the smaller box is 32 newtons. Part C, determine the velocity of the boxes after 4 seconds. So once again, this has become a kinematics problem because we know the rate of acceleration now, and now we're dealing with another sort of like kinematics quantity in terms of the time. Remember, we need something else. We always need 3 quantities in order to solve a kinematics problem. So think to yourself, what is the third thing that we know? Okay, so we know the initial velocity is 0. That was given in the question, that the boxes are starting from rest. So we know that, we know the acceleration, and we know the time. And we're trying to find the final velocity after 4 seconds. So once again, you just have to go look in your formulas of kinematics, pick the right one. And in this case, it's this one. The final velocity equals the initial velocity plus the acceleration times the time. Plug in the numbers, and you should get a final velocity of 6 meters per second, which makes sense because if you just look at the acceleration, it's basically saying the speed increases by 1.5 every second, and it goes for 4 seconds. So you just multiply that by 4. That formula, oops, I wrote a 5 here. That should be a 4. All right, so just to summarize, here are the main points, kind of. A dynamics question can turn into a kinematics question, and this is usually how it happens. So first you draw a free body diagram of some scenario that involving forces, and you solve for the acceleration of the object using Newton's second law and by thinking about the net force. And once you know the acceleration, then you can use that in kinematics formulas because that's one of the key quantities of kinematics. So obviously you would have to know a couple other things as well, such as time, distance, or velocity. But if you do know those things, then solving for the acceleration by using Newton's second law is often the part that unlocks being able to do the rest of the question and solve for the other components of the motion of that object.